Okay, welcome to lecture number 15, beginning discussion of matter and heat. First, I want to talk about temperature scales, Fahrenheit, Celsius, and Kelvin. Textbook and everything we ever see has the conversions given by these equations, which appear to be magic. Most instructors do not explain where this 5/9 or 9/5 come from, so let me try to explain, okay? The Fahrenheit and Celsius scales both are based on water, the freezing point and boiling point of water. So we know that degrees Celsius, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And so we can consider 100 steps between boiling and freezing, 100 steps. You'll see why I call them steps in a second. Fahrenheit scale, we know that water freezes at 32 degrees Fahrenheit. How many people know what temperature it boils at? No, most people don't. Well, anyway, the answer is 212 degrees Fahrenheit. Okay? How many steps between boiling and freezing? Well, 212 minus 32 is 180 steps. Okay? So why am I calling them steps? Well, let's consider. Let's use our imagination. 1 second. Imagine this is a building, and there's 100 steps to get to the top floor. Here's another building, same height as the first building, but instead of 100 steps, there's 180 steps. My question to you is, which steps in which building are larger? Steps in the Celsius building or the steps in the Fahrenheit building? Now, hold on 1 second. I'm going to change this 180 to 200 just for a second. We'll go back. I'm going to say, imagine there's 200 steps in this building and there's 100 steps here. And now I ask the question, in which building are the steps greater? Well, it's clear that Celsius only needs 100 steps to get to the top. The Fahrenheit building needs 200 steps. So we would say that the Celsius steps are twice as big, or twice as great, as the Fahrenheit steps, because 100 to 200. But I fudged, right? I said 200. Suppose this is 180 steps. Now, what steps are larger? Well, the Celsius steps are still larger, greater than the Fahrenheit steps. By how much? Well, it's not quite 2 times greater. Instead, it's 1.8 times greater. So here's what I'm saying. I'm saying 1 degree Celsius is 1.8 degrees Fahrenheit. If you change the temperature by 1 degree Celsius, how many degrees have you changed the temperature Fahrenheit is 1.8? Well, if you're an expert in fractions, you know that 1.8 can be written as 9 over 5. 5 into 9 is 1, remainder of 4. 5 into 40 is 0.8. Okay, so 1.8. 9/5, there's the 9/5, which is really 1.8. So it's a matter of converting. So 1 degree Celsius, or 1 step in the Celsius building, is equal to 1.8 or 9/5 of a degree in the Fahrenheit building. Okay? And why is there a 32? It's clear. 0 degrees Celsius is equivalent to 32 degrees Fahrenheit. So you have to shift the origin by 32, depending on which way you go, plus or minus. If you go the other way, instead of 9/5, you have 5/9. You flip it. Okay? Now, listen to my question. Pay attention to the words. Pay attention to how you read questions. Okay? It's critical. If I ask a question, 53 degrees Celsius is what temperature Fahrenheit? Well, what I do is I put 53 in here, multiply by 9/5, and add 32. That would tell me the temperature Fahrenheit. Okay. Suppose I ask the question, a change in temperature, listen, a change in temperature of 6 degrees Celsius is equal to a change in temperature of what equivalent amount in degrees Fahrenheit. So in other words, I'm going to summarize. I'm going to say, if delta T equals 6 degrees Celsius, what is delta T in degrees Fahrenheit? Okay, this would be my exam question. Well, we just said that 1 degree Celsius is 1.8 degree Fahrenheit, right? A change of 1 degree in Celsius is equal to a change of 1.8 degrees in Fahrenheit. So what if I take a 6 degree change? So all I'm doing is multiplying this equation by 6. 6 times 1 degree Celsius has to be equal to 6 times 1.8 degree Fahrenheit. Now, before you reach for your calculators, forget the calculators. Let's go. Let's connect some neurons, shall we? 6 times 1 is 6. 6 times 8 we know is 48. So 6 times 0.8 is 4.8. So now we add 6 plus 4.8 is 10.8 degrees Fahrenheit. If you change the temperature by 6 degrees Celsius, you've changed the temperature by 10.8 degrees Fahrenheit. Okay? Let's do another one. Delta T equals 8 degrees Celsius. Delta T is what degrees Fahrenheit? Same problem. 1 degree Celsius is 1.8 degrees Fahrenheit. So 8 times 1 degree Celsius is 8 times 1.8 degrees Fahrenheit. Again, let's do this in our heads. Let's try. 8 times 1 is 8. 8 times 0.8 is 6.4, right? 64, 8 times 8. So we have 8 plus 6.4 is what? 14.4 degrees Fahrenheit. So the answer would be 14.4 degrees Fahrenheit. You are free to use your calculator. Using your calculator takes more time. If you can do this in your head and connect neurons, you'll be in a lot better shape than not doing it in your head. Okay, I want you to practice. Practice doing things rapidly. Doesn't matter if you get them correct the first time. Try to do things as quickly as possible and try to estimate. Okay? All right, let's move on. What I want to talk about now is something called specific heat capacity. Specific heat capacity. Oh. All right, let's look at the word heat. What is heat? Man, that's a great question. For now, and what our textbooks calls it, we're going to say that heat is energy in transit, whatever that means. Okay? Energy in transit. It's energy moving. Okay? So heat is going to be energy. Heat is energy. I'm going to write this. Heat equals energy. Now, we had a unit of measuring energy. If you remember a couple lectures back, we measured energy in something called joules. So, can we measure heat in joules? The answer is yes. Of course we can measure heat in joules. Unfortunately, historically, the people who studied heat did not measure heat in joules. They used another unit called a calorie. So we're going to define a calorie. 1 calorie, and I want you to note that's a small c calorie. 1 calorie is going to be equal to 4.2 joules. It's a conversion. It's like saying 1 inch is 2.54 centimeters. It's just different units. For heat, again, traditionally, historically, we're going to use calories. But I just want you to know it's related to joules. It's just a unit of energy. Now I said small c is this. What is 1 calorie with a capital C? 1 calorie, I made it very big, is equal to 1,000 calories. Sounds strange, doesn't it? 1 calorie is equal to 1,000. 1 calorie with a capital C is equal to 1,000 calories with a small c, or 1 kcal. What is K? It's kilo, right? Kilo, 1,000. Kilocalories. So food calorie is a capital C. Food calories equal to 1,000 of these calories. So we're going to be using mostly calories. We could convert to joules, but for this class, I'm not converting to joules. Everything we do with heat is going to deal with, well, we're going to use the units of joules, okay? Of calories, sorry. Specific heat capacity, specific heat capacity. What's specific about it? All right, let's talk words. What I'd like to do is use words and then convert these words into an equation, okay, to show you that it's not that confusing. All right, all right. Everybody imagine that this eraser is a piece of copper. Piece of copper. Suppose I add 100 calories of heat to this piece of copper. What would happen? Again, no tricks. You know when you add heat to something, put a flame, add heat. If I add 100 calories of heat to this, the block would get hotter. There would be a change in temperature. So I'm going to write change in temperature, delta T. This is change in temperature, okay? My question is, what does the change in temperature, what does the change in temperature depend on? Well, we just said if I add 100 calories of heat, the temperature goes up. What if I added 200 calories of heat? I think the temperature would increase more. Or 1,000,000 calories of heat, the temperature would go way up. So the change in temperature is directly proportional to the amount of heat that you add. I'm going to use the symbol Q. Q is going to be the amount of heat. Amount of heat, energy. Okay, let me take calories out of here. Remember, the amount of heat energy is going to be measured in calories with a small c. The greater the amount of heat you add, the more the temperature goes up. Now, instead of a piece of copper this size, suppose I took a piece of copper the size of a desk. Okay, really big piece of copper. Now suppose I add 100 joules of energy, heat energy. I keep saying joules. 100 calories of heat to a piece of copper the size of a table. 100 calories of heat to a big piece of copper. Will the temperature go up? And the answer is yes, it'll go up. My question is, will the temperature go up as much as it did for a small piece of copper? And the obvious answer is no. The greater the mass, the more mass you have, the smaller the change in temperature. How do we say that mathematically? We put mass in a denominator. The greater the mass, the smaller this number. Okay? One other factor that determines how much the temperature changes. How much heat you put in, calories, certainly affects the temperature change. The mass of the object certainly affects the temperature change. What else affects the temperature change? What if this was not made of copper, but instead was made of aluminum? If I add 100 calories of heat, 100 calories to a piece of aluminum this size, you agree that the temperature will not change exactly the same as if I had if I had a piece of copper, or if I had a piece of iron. So somehow it's going to depend on what the material is made of. Okay? I'm going to put a C here. This C is called the specific heat capacity. And it depends on the material. Okay? It depends on what your material is made of. Great. Now, let me define calorie. We know it's a unit of energy, but how is it defined? Well, it's related, it's 4.2 joules, we know that, but how do you define a calorie? Okay? So I want to try to define what a calorie is, okay? Technical difficulties. Okay, let's go on. So how do you define a calorie? Here's how we're going to define a calorie. 1 calorie is defined to be the amount of heat or the amount of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is the amount of heat required to raise the temperature of water, 1 gram of water by 1 degree Celsius. So the specific heat capacity, C sub W, what does W stand for? Stands for water. I'll put water here. Is this. We'd write this as 1 calorie with a small c per gram per degree C. Does everybody see what I've done? The specific heat capacity for water is 1 calorie per gram per degree C. Now, what's the specific heat capacity? C for copper. I don't know what it is. I'll make it up. I'll make up a number. Don't use this. Suppose the specific heat capacity of copper is 0.2 calories per gram per degree C. If it was 0.2, what does this mean? This means that it only takes 0.2 calories of heat to raise the temperature of 1 gram of copper by 1 degree C. What about aluminum? Again, I'm making this up. The specific heat capacity for aluminum is going to be 0.1374 calories per gram per degree C. Is it really? It's not really this number. I'm making it up. What does this mean? This means it takes 0.1374 calories of heat added to 1 gram of aluminum will raise the temperature of that 1 gram of aluminum by 1 degree C. So that's what specific heat capacity means, okay? For water, it's 1 calorie per gram per degree C. For these other elements, you have to be given or you have to calculate it from a problem, okay? So let me erase this and go back to our equation for specific heat capacity that we were talking about. We wrote delta T is equal to Q divided by the mass and then the C, specific heat capacity. Okay, I like to rewrite this in this way. Q equals MC delta T. Well, mind you, MC hammer, right? The wrapper equation. Q, calories. M, grams, usually. This is calories per gram per degree C. Then delta T would be degrees C. Okay, so we're going to use this a lot. Let's do a problem. Okay? By how much does the temperature change if 20 little c calories of heat are added to 10 grams of element X whose specific heat capacity is 0.25 calories per gram per degree C. Okay? So what do we need? We need this equation. Q equals MC delta T. What are we trying to find in this problem? By how much does the temperature change? So we want to find delta T. And what that means algebraically is we have to solve for delta T. I'm going to solve for delta T. Q equals MC delta T. I need delta T by itself, so I'm going to divide by MC. Divided by MC. Okay? So we have that delta T is equal to Q divided by MC. The units remaining had better be just the temperature unit. Here, hopefully, degrees Celsius. All right, let's look. What was the heat? What was Q? How much heat was added? I said 20 calories. 20 calories with a small c. What is the mass? I said 10 grams. 10 grams. What is the specific heat capacity? 0.25 calories per gram per degree C. 0.25 calories per gram per degree C. Okay? I believe what is that? 2 times 1/4. Is that 8? Is the answer 8? 8. Notice calories go out, calories go out. Grams, grams. We're left with degrees C. So I think 8 degrees C. 8 degrees. So 8 is the temperature change, okay? So all of these problems dealing with specific heat capacity are simply plugins to this equation. Remember, whenever you're given an equation, whenever you're giving a problem, you know everything in that equation except for one thing, and that's the thing you need to solve for. We're given the heat in this problem, we know the mass, we know the specific heat capacity of element X. We're asked to find delta T. Make sure your units are correct and everything will cancel, and it's just a matter of plugging in. Okay, we'll continue with this in the next lecture.